Okay, so it's a great pleasure to welcome everybody to the first CMSA Tsinghua Math Science Literature Lecture of this academic year. This is a joint venture of the CMSA here at Harvard and Tsinghua University, a series initiated by Xing-Tung Yao several years ago. And we'll have this lecture this fall on Zoom. There will be 2 lectures in the spring. They will be announced soon. And it's a great pleasure to turn it over to Yao, who will introduce our speaker.
Well, Greg, thank you very much, Dan. It was a great thing to see you, although in Zoom. I was a former director. Now we have a great new director. I'm sure he's doing much better job than me. But in any case, I did start this program, which I'm rather proud of, because many great scientists and mathematicians did speak in this series of lectures, and many of them are outstanding. And so I'm very happy when Dan proposed Scott Kominer to give these talks, because Scott has been working affiliated with CMSA since 2015, many years. Almost every year he has been helping to organize the big data conference and all that, and has been one of the most important mathematician and economics associate to us. So I think, well, mathematics and economics, game theory and all that are really exciting area. The methods could be used for many other purposes besides commercial use. And I've been looking into that, and I think it's very interesting. And Eric Maskey did give some talks last year, and I think it's very influential. And today we have Scott to talk about 60 years of matching, from Gale and Shapley to trading networks. I think this will be exciting. So Scott, let's start.
Thank you so much. I'm incredibly honored to be here today. First of all, I should say this is a real, in many ways, it's a homecoming. For the CMSA has been incredibly essential and integral in my own development as a scholar, and the work I do, bringing math and economics and operations research and computer science all together to try and redesign real world marketplaces. And this talk is sort of going to really frame around that type of evolution and cross interplay between math and many other fields. I should also say this is a homecoming because I was just thinking about this literally like 4 minutes ago. Yao was chair of the math department when I first read the paper that is going to be the center of the discussion today. And so it's extraordinary. Like, you know, I can't even like quite describe the experience of being here to now teach this, you know, before my former department chair, you know, sort of, you know, as we go into Gale and Shapley. So this is going to take us through 60 years of matching. We're going to spend naturally a little bit more time at the beginning than at the end. We'll speed up as we go. But just to start with, let me frame in the backdrop. This is a talk about market design. And market design translates economic theory and analysis into practical solutions to real world problems. It's sort of a branch of economics that takes theory and uses it to better understand market failures and then design solutions. You know, I was once asked, you know, how would you describe this to a 6-year-old? It's like, the driving question of market design is, how should the world work, right? If you could design it, how would you make it run better? And as such, there's this extraordinary interplay between theory and practice, sort of taking math and using it to better, you know, shape the world, evaluating sort of what happened, whether it worked, and then that all feeds back both into sort of practical, you know, innovations and improvements, and then also, as we'll see today, into more beautiful mathematics. So it's a little bit like, you know, one of these, you know, sort of golden spirals, but really even more, it's like a chambered nautilus. Sort of at each layer, you discover there's sort of like an infinite depth to explore. So one branch of market design, many you would say, starts with Gale and Shapley, 1962. This is one of, if not the most heavily, one of the most, if not the most heavily cited paper in the history of the journal, the American Mathematical Monthly. And it's actually an incredibly readable paper, even today, right? There's so much in it. There are many, many things in it, even more than we'll actually get to talk about today. But it's also just something you can hand almost anyone to read and sort of appreciate this mathematics. So I'm going to do the unusual thing of starting the talk by literally reading some of the paper to you. Oops. But first, let me quickly say, one really cool thing about putting this together was I got to see some of the early working paper editions. So this is the Rand, the Rand Corporation version. And then Dick Gross emailed me the unclassified, I guess the Office of Naval Research version. We're looking at Gale Shapley 1962, the final form as it appeared in the journal, but here already it took form in 61, and in fact in 60, a very you can walk through the drafts and I don't know, it's beautiful, really exciting. Okay, so let's read. The problem with which we shall be concerned relates to the following typical situation. A college is considering a set of N applicants of which it can admit a quota of only Q. Having evaluated their qualifications, the admissions office must decide which ones to admit. The procedure of offering admission only to the Q best qualified applicants will not generally be satisfactory, for it cannot be assumed that all who are offered admission will accept. So this is a problem that should be familiar perhaps to everyone on this on this stream. Right? College admissions is about matching. Schools choose students and students choose schools, and just because you want to go to a school doesn't necessarily mean they will choose you, and just because a school admits you doesn't necessarily mean you will go. And so you could imagine instead, and Gale and Shapley imagine a universe in which we try and somehow solve this problem in an efficient, in a simple way, right? And instead of having schools admit 15 students, each student gets admitted by 15 schools, and then they have to think about where to go. You could imagine that the students are going to just tell schools, like, I really want to go to you, or tell the system, sort of where they'd like to go, maybe in rank order. But there are some challenges. The usual admissions procedure presents problems for the applicants as well as the colleges. An applicant who is asked to list in his application all other colleges applied for in order of preference may feel, perhaps not without reason, that by telling a college it is, say, his third choice, he will be hurting his chances of being admitted. And so they go on to sort of describe this problem, and say, like, look, at some level, the problem's obvious, right? If you have students with preferences over schools and schools with preferences over students, you just make the assignments in accordance with those preferences. A little reflection shows that complication, though, may arise. An example is the simple case of two colleges A and B and two applicants, alpha and beta, in which alpha prefers A and beta prefers B, but A prefers beta and beta prefers alpha. Here, no assignment can satisfy all the preferences, right? There's sort of opposite preferences. The schools, sort of like more the students that like them less. And so you could imagine one thing, the students, sort of go to the schools that they like the most, or another, the schools take the students that they like the most. These are different outcomes. And Gale and Shapley set up a design goal. They say, what we would like, that the following should not occur. An assignment to applicants is called unstable if there are two applicants, alpha and beta, who are assigned to colleges A and B, although beta prefers A to B and A prefers beta to alpha. We don't want a circumstance where where a student and a school would mutually prefer each other to their assigned matches. Gale and Shapley go on to sort of simplify the problem, to start to analyze it. In trying to settle the question of the existence of stable assignments, we were led to look first at a special case in which there are the same number of applicants as colleges and all quotas are unity. This situation is highly unnatural in the context of college admissions, but there's another story, and it's story in scare quotes, because this is actually not going to be a perfect model of that context by far, which it fits quite readily. A certain community consists of N men and N women, and how do we establish marriages that is stable? In the sense that First, every man or woman is matched to an acceptable partner, and there's no pair who mutually prefer each other to their assigned matches. And so through that, Gale and Shapley set up what has become one of the most foundational frameworks in market design. And it starts with just this one-to-one stable marriage problem. And again, as I say, this is actually not a great model of marriage. First, not only is it too heteronormative for, sort of to be a meaningful description of the marriage market in practice, but as we'll see, there are lots of other things that are not quite right about this model for thinking about marriage. We're going to stick with it as we're setting up the math. And then as we'll see very quickly, it's not a great model of marriage, but it actually is a pretty good model of things like centralized labor markets, medical residency matching, school choice, many other contexts. So given a set of men with preferences over women and women with preferences over men, we say that a marriage matching mu, and this is just going to be a function that matches men to women and vice versa, is stable if first it's rational, all agents find their matches acceptable, and unblocked. There's not a man M and woman W such that both W, this notation here means preferred, so W prefers M to her assigned match, and M prefers W to his assigned match. So there's not a man and a woman who mutually prefer each other to their assigned partners. Now, it's not at all even obvious that such a thing exists, right? Like, I've defined a solution here, stability, or a goal, an objective, stability, but I haven't said that there are stable matchings. We'd of course be, this would be a short talk if the answer were, set of stable matching or marriages is empty. And indeed, in fact, sort of miraculously, it turns out that a stable marriage matching does exist. And sort of the first main result of Gale and Shapley is the existence result. And not only is it an existence result, it's actually constructive. So they prove existence by giving a procedure for actually finding a stable matching. And this is called the deferred acceptance algorithm. How's it work? So you can imagine all the men lined up on one side of the room and all the women lined up on another. And again, as I say, this is sort of, an abstracted mathematical model of marriage. It's not actually a good model of the marriage market. But here we're doing sort of two-sided matching because again, it's going to be, students and schools, for example, and it's eventually, and it's very uncommon for schools to marry each other. So each man walks across the room and proposes to his first choice woman. Each woman holds on to her most preferred acceptable proposal, if any, and rejects all others. So, note some women just got lots of proposals potentially. Each one holds their best acceptable proposal, if any. If they didn't get any acceptable proposals, they reject all of them. They hold but if there's any of them, they hold the best one. And again, it's hold, it's not accept. We're deferring the acceptance step, as the name suggests. And then in future steps, each rejected man now walks across and proposes to his next highest choice woman, and each woman holds on to her most preferred acceptable proposal, if any, and rejects all others. And we iterate through this process. And if you note, as we go, sort of the men are moving down their preference lists, and the women are getting better and better proposals over time. I claim at the end of the algorithm, and so it's got to end at some point because the men eventually run out of women to propose to. They're either all on hold or they've proposed to everyone, that they find acceptable. I claim that at the end of the algorithm, we obtain a stable matching. So how do we prove that? First, individual rationality. How do we prove that no one has an unacceptable partner at the end? Well, that's easy. First, men only proposed to women that they found acceptable, and women only held acceptable proposals. So everyone has an acceptable partner at the end of the algorithm. And now how about that, no rematching? So there's no blocking pairs. There's no man and woman who mutually prefer each other to their assigned matches. Well, let's suppose for the sake of contradiction that there were. So there's a man and woman who mutually prefer each other to their assigned match. But then something must have gone wrong, right? Because the men were proposing in order of preferences. And if he proposed, then he must have proposed to that woman somewhere along the algorithm, right? He prefers her to the woman he ended up with, and he was going down his list. So he proposed to her at some point. But at every step, the women held their most preferred acceptable proposal. And so if she ever rejected him, she must have gotten a proposal she likes more. And so we have a contradiction. Either the fact that he proposed is false, so he doesn't prefer her, or the fact that she rejected him is false, or rather the fact that she held him is false, so she doesn't prefer him. So there's no man and a woman who mutually prefer each other to their assigned partners under deferred acceptance. And so that's like a miracle in and of itself, right? Like the fact that we can find these stable matchings, totally non-obvious ex ante. Also, by the way, it's kind of a fast algorithm. It runs in quadratic time. We only have to, at worst, every man has to propose to every woman in sort of like, their own individual round. But there's more. The deferred acceptance outcome actually produces your most preferred among all stable outcomes. So every here you sort of expressed in the college admissions language, but every applicant is at least as well off under the assignment given by deferred acceptance as under any other stable assignment. And the argument here, which I've got on the slide, if you're watching this in video later, feel free to like stop and consider it, or again, just read the Gale. This is in the Gale Shapley paper again. The argument is very elegant. It's a simple sort of inductive monovariant argument that looks at the outcomes that are achievable. So, it turns out that your deferred acceptance partner is your best possible partner across all stable matches. So it's the best partner you can achieve in any stable match. And you can show that sort of what's going on is you're sort of never rejected by a partner that you might have in some stable matching. So that's all 1962. We just, we just spent about 7 minutes and we're not even done with the Gale Shapley paper. But quickly to zigzag, so that, or to elaborate, I suppose, that observation about side optimal stable matching was very soon after generalized by Conway. It's in Knuth cites it to Conway. Luckily, there's an English translation version, so I was able to read this in the original too, or the translated original. I unfortunately do not speak French, even mathematical French. But so it turns out that there's not just a side optimal stable matching, but rather the set of stable matchings has a lattice structure. So given any two stable matchings, mu and nu, there's a stable match that every man likes weakly more than mu and nu. And indeed, sort of as you'd guess, the opposite is true as well. Given any two stable matchings, mu and nu, there's a stable match that every man likes weakly less. So you can sort of move in a man-preferred direction in the stable matching lattice, and you can move in a man dispreferred direction in the stable matching lattice. Moreover, there's opposition of interest. So if all men weakly prefer stable match mu to stable match nu, then all women weakly prefer nu to mu. So if you're moving in the man-preferred direction, you're actually making the women systematically worse off and vice versa. Quick footnote, how do you prove this? It's actually, again, it's very elegant, at least in the context of the marriage problem. So the way to do it is to sort of say, give me two stable matchings, mu and nu, and ask every man, okay, point to your more preferred partner between these two matchings. And there's sort of a miracle that happens, another mathematical miracle, which is that every man is pointing to a different woman. Why is that? It turns out to be a consequence of stability. If two men were pointing to the same woman, well, they both prefer her to their partners in their other potential partners in these matchings, but she must prefer one of them. We assume strict preferences. And so, suppose she prefers her partner in mu. Well, he prefers her to his partner in mu and nu, and she prefers him to her partner in nu. And then we found an instability in mu. And this argument also, incidentally, sort of explains why this third bullet point is true. So if you're picking the sort of the man preferred outcome, you're sort of moving in a direction where the women are in effect getting less choice in the allocation. And indeed, remember, we have endpoints. So not only do we have this matching, this matching lattice that we can move around, but there's a stable matching lattice we can move around. But deferred acceptance is the endpoints. So man and woman proposing deferred acceptance are sort of the most man preferred and the most woman preferred stable matching. And sort of in general, we can move around via this lattice operation. So very simple example. Here we have just a market with 2 men and 2 women, M1 and M2, and the men like women with the same numbers, and the women prefer men with opposite numbers. So, we can run deferred acceptance with the men proposing. Man 1 proposes to woman 1, man 2 proposes to woman 2. They're both acceptable, so their proposals are held, and bingo, we have the man optimal stable match already. See, not so bad. Similarly, we could run woman proposing deferred acceptance. Woman 1 proposes to man 2. Woman 2 proposes to man 1. Again, these partnerships are acceptable, and so they hold, right? Man 1 holds woman 2, man 2 holds woman 1, and we have the woman optimal stable match. And so even in this very simple 2x2 example, you can already see opposition of interest, right? We have, just opposition of preferences leads us to, 2 different stable matchings. It's a small lattice. It only has 2 points in it, but those, but they are distinct. And in general, you can potentially have many. But there's something else really interesting about this example, which is that it implicitly shows a consequence of opposition of interests, which is, let's imagine for a minute that woman 2 pretends that man 2 is unacceptable. So if man 2 proposes, she's going to reject him. So now what happens under man proposing deferred acceptance? So man 1 proposes to woman 1, man 2 proposes to woman 2, woman 1 holds man 1, woman 2 holds man 2, rejects man 2. Man 2 comes back and proposes to woman 1. Woman 1 now holds her best acceptable proposal, which is now man 2, and rejects man 1. Man 1 comes back now and proposes to woman 2, and instead of getting the man optimal stable match, we actually get the woman optimal stable match. So woman 2, but we're imagining, of course, like this process isn't really happening with like men and women standing in different sides of the room and proposing to each other. This is actually really happening, we're imagining in some centralized system that takes in everyone's preferences. But we've just learned something about such a system, which is that there might be an incentive for at least one side of the market to manipulate their preferences, to not be fully truthful in specifying their preferences to the mechanism. Right? If the system is implementing the man optimal stable match, it's implementing man proposing deferred acceptance, then if woman 2 lies about her preferences and tells the mechanism that she only finds man 1 acceptable, then she gets man 1 instead of man 2, because man proposing deferred acceptance then leads actually to the woman optimal stable match. So there's a real design subtlety if you're implementing a stable matching mechanism, right? Not only are you sort of implicitly choosing one side to favor over the other if you run deferred acceptance, right? Are you favoring the men or the women or the students or the schools? Which side of the market are you favoring? But in fact, there's no mechanism that is strategy proof that incentivizes truthful preference revelation for both sides of the market. And at best, you can incentivize one side. So the side optimal stable matching mechanism makes it optimal for, this actually uses the unit demandness as well. So we got to state in the marriage language, the man optimal stable matching mechanism makes it a dominant strategy for each man to state his true preferences. And, conversely, the woman optimal stable matching mechanism makes it a dominant strategy for women to state their true preferences. But so, neither side is guaranteed to be incentivized. So neither side is always going to be incentivized to state their true preferences. The best you can do is incentivize the proposing side. So now, not only when you implement deferred acceptance are you choosing a side to, sort of favor in the outcome, but you're also choosing a side to give potentially easier strategic incentives to. And again, by the way, this is all math so far, right? One of the things that's like extraordinary to me about how matching theory developed is these questions are in dialogue with various matching contexts in the world. But at some level, like these were mostly being proven as mathematical theorems. Like the Dubins and Friedman paper is called something like Machiavelli and the Gale Shapley algorithm, right? It's sort of asking the question, like, okay, like, you know, we've got this matching procedure. What incentives does it create for participants? But this is theory. And as we'll see very soon, it's theory that has rather significant implications for the world. But one more theorem before we go there. This is called the lone wolf theorem. The title is more recent, but the original version of this is a paper by McVitie and Wilson. And this is a very elegant invariance result and shows the set of matched men is invariant across stable matching. So we've said there's this lattice, right? There's like a lot of different stable matchings potentially. You might ask, are the set of, can we, pick a matching to like make certain men like matched where we couldn't otherwise, right? If we want to favor a particular group of men, can we find the matching that makes sure to match them? And the answer is in some sense, no. Like you can favor by moving around points in the lattice, but you can't change, you can only favor so much. Anyone who's unmatched in some stable matching is unmatched in every stable matching. And how does that work? It's an argument so elegant, I can do it on a slide with basically a single diagram. This is the closest we'll get to a commutative diagram in this talk. So let mu bar be the man optimal stable match and mu any other stable match. And I'm going to abuse notation slightly. I'm going to use sub m to be the set of men matched and sub w to be the set of women matched. So we're just going to compare the set of men matched under mu bar to the set of men matched under mu, and similarly the set of women matched under mu bar to the set of women matched under mu. So first, because mu is the man optimal stable match, we know that there must be weakly more men matched under mu bar, right? So the set of men matched under mu bar has to be a strict or a weak superset of the set of men matched under mu. And then going back to that Conway lattice theorem, making the men better off means making the women worse off. So the women must all prefer mu. Excuse me. And so the set of women matched under mu must be weakly larger than the set of women matched under mu bar. We're done. Why is that? Well, it's one-to-one matching. Every agent has a single partner. And so the cardinality of these sets is the same, and the cardinality of these sets is the same, right? Every man has one woman they're matched to. Every woman has one man they're matched to. And so these are the same size. That means that these weak inclusions actually have to be equalities, right? We can't have a larger set here that's, the set here that's larger than this set, which is the same size as this set, which is larger than this set, which is the same size as the one we started with. And so as a result, we see that, mu bar m and mu m have to be the same. Similarly, mu bar w and mu w are the same. The set of matched men and women are invariant across stable matchings. This kind of the other thing that's really cool about this to me, like when I first learned all of this, I was just like totally shocked at how much structure the very simple constraint of stability imposes, right? That pointing argument we made uses just stability to get this very, very rich lattice structure. And then lattice structure spits this out immediately, right? This is like just a consequence of that like opposition of interest results, which comes from the lattice. And yet these are powerful statements. If I wanted to choose a stable matching mechanism in order to like improve the likelihood that a given group was matched, can't do it. Returning to Gale and Shapley briefly, I explained deferred acceptance just in the context of the marriage problem, but as Gale and Shapley note, everything there generalizes to college admissions. Although note they're using a specific model of college admissions where they're imagining the school has a single rank order list and takes the best set of students it can according to that list. This is what are called responsive preferences. But in that model, deferred acceptance just sort of carries over directly. And the proof the assignment is stable is entirely analogous to the proof given for the marriage problem and is left for the reader. So we'll leave that to the listener. That's actually a good place to pause for a second because we're about to go from theory into practice. So any questions on the sort of the mathematical setup that we just put together? Going once, twice. All right, sold. So let me now sort of deconstruct a little bit of the framing of the marriage problem, right? We had a society with a set of men M and a set of women W. We're trying to find a stable marriage matching, and we made a lot of assumptions. So I didn't belabor this at the time, but we assumed strict preferences, right? So we assumed that, you know, the ranking, the men's ranking of the women and the women's ranking of the men are strict rankings. We assumed bilateral relationships, so only pairs and possibly singletons, people who don't get matched. We assumed the market was two-sided, right? As I said, you know, as I flagged earlier, like, you know, we were sort of assuming that we were just matching men to women and vice versa. And we assumed that the preferences are fully known. So we assume that, you know, everybody knows their strict preferences over all people in the market. So these are pretty difficult assumptions. We already talked, by the way, about why this two-sided thing is also like not a great model, you know, assumption for the marriage market. But conceptually, even if you had like a one-sided or a multi-sided market, these other two assumptions are really hard to think about in a context with a market as big as marriage. Moreover, there's a hidden assumption. We didn't like frame it as an assumption of the model, but there's a hidden assumption of centralized market clearing. We're sort of imagining that the entire market clears in a single step when we run the deferred acceptance algorithm. That's also not a thing that we're sort of used to in the marriage market, where the marriage market clears over time. And in part, that's because, you know, people generally don't know their full preferences and might be learning them as they go along. You know, but just like imagine for a second, right? If we were trying to do centralized matching at the level of a country, maybe as a market, right? So like, you know, the US population, you have to specify your full preferences over all potential match partners. Those are going to go into this centralized simultaneous market clearing process. You're going to rank, you know, sort of 100 million people or something. How do you don't know your preferences, much less like necessarily have a way to like break ties between people who are like very close and, you know, closely similar, much less when you get to a market the scale of China or something of the sort. So this is like really not a very good model of the marriage market, right? Not only is it sort of absurdly heteronormative, but it also just like at some fundamental level, like the data that is the input to the model isn't a thing that we think of as present in the marriage market. And the centralized market clearing is just like not a good description of reality. But these are not at all absurd assumptions for thinking about centralized labor markets. In fact, if anything, they might be just like true. And as it turns out, in at least some labor markets, they were. So in a really beautiful paper in the mid-80s, Al Roth observed that the medical residency matching process in the United States, which had been centralized since the 1950s, was in fact using not exactly Gale Shapley, but a version of stable matching that was equivalent to the Gale Shapley algorithm, and had been doing it for a decade before Gale and Shapley's paper. And so not only are these like reasonable assumptions for thinking about some labor markets, but medical residency matching was basically using this model. They just didn't know it. There wasn't mathematical formalism for it, and even if there had been, like, nobody noticed for another 20 years. And this is like, you know, sort of totally extraordinary at some level, right? It was like Gale and Shapley were writing, and the language suggests as if this is sort of like, this is a thought exercise, sort of an exercise in mathematics. But here at the same time, Roth was discovering that it was an exercise in the world. And what was going on? Well, since 1952, the American medical associations had been running a centralized match to match doctors to the residencies. Why does it make sense to have a centralized labor market? Like, what does it even, why is this labor market centralized? Well, people go into residency in tranches, right? You finish medical school and then you go to residency. And so people were all entering the labor market at more or less the same time, right? Commencement is a slightly different, week or whatever from school to school, but to a first order, doctors were finishing medical school and then all going into residency sort of in these waves, sort of like students starting college admissions. And we'll go into the reasons in a little bit, but the market had been centralized and organized through a central clearinghouse. And as Roth showed, the algorithm that had been in use since the 1950s was in fact producing the hospital optimal stable outcome. It was equivalent to hospital proposing deferred acceptance. And how equivalent is it? Well, the main proof of this argument, in effect, shows a correspondence between what's going on, and so it sort of shows stability, and then infers a correspondence with Gale Shapley. So Gale and Shapley were unaware of this procedure at the time. Presumably, also the American Medical Association's I think it was called the National Intern Matching Program at the time, were unaware of Gale and Shapley, but here sort of parallel evolutions were leading to stable matching. Now, quick question, footnote maybe, is why did they have a centralized match, right? Well, what would most labor markets are not centralized, and yes, okay, so medical residency sort of all happens at the end of medical school, but private equity jobs happen at the end of college or MBA or whatever, and we don't see centralized labor markets for that. Law, sort of first-year associate positions in law, happen right after law school, right? There are lots of people who go into the labor market in a centralized way. We don't have centralized matching systems, but something very specific had been going on in medicine, which was first unraveling and then congestion. So the unraveling is a little bit easier to explain, and many of us have experienced it in some labor market context. What was happening was, in order to lock in candidates, residency programs were making offers earlier and earlier and earlier, right? So you make your offer like a week ahead of everybody else. And you tell the candidates, hey, you've got 6 days to decide. Now, suddenly, those candidates might be thinking, well, this is an offer from my second choice hospital. I don't know if I'm going to hear from my first choice. You call your first choice hospital, you say, hey, can I, I've got an offer from this other hospital, but I'd really like to work with you. And they say, great, thanks so much for letting us know. We're processing applications as quickly as we can. We'll get back to you as soon as possible. And on day 5, you call and say, hey, any news? And they say, we're really sorry, we don't know yet. But please stay open. We're keeping track. We know about you. Day 6, maybe you sign with your second choice hospital because, a bird in the hand is good. And then maybe on day 8, you get a call from your first choice hospital. Oh my gosh, we're so sorry that took so long. But we hope you're still on the market. And, you have to say, gosh, I'm so sorry. I took the other offer. Footnote, presumably some people also broke their original contracts and said, sure, I'm there, then called their second choice hospital and said, oh my gosh, so sorry. Just discovered my spouse can't stand Boston. And they're like, aren't you at school at Harvard? Did you not know this? And they're like, no, sorry, gotta go. But more and the sort of, I don't know, the proper, sort of the, I'll make a slight value judgment and say sort of the honorable strategy is to say, look, I'm so sorry. I already took the other offer, and your first choice hospital says, no, thank you so much. We totally understand. We're sorry we couldn't get back earlier. They hang up the phone. They're so annoyed. Oh my gosh, I can't believe it. That's stupid hospital number 2. Next year, we'll make our offers 1 week ahead of them. And gradually this process unravels until doctors are accepting residency offers before they've even chosen their specialties. And so you might take a job as a surgeon and then discover later that you pass out at the sight of blood. And this is bad. Everyone agrees this is bad, but the problem is it's equilibrium, right? Everyone agrees the offers should be later, but conditional on when they're making their offers, you want yours to be just a little bit earlier. And so the market unraveled consistently for, better part of 50 years. And then the American Medical Association started trying to figure out how to organize it. And the first thing they did was sort of impose a set of rules and tried to sort of like force all the offers into a very narrow time band. But that was chaos too, because now sort of this same sort of process is happening, but in a very congested fashion where like people are like getting 2 minutes to make decisions and so forth. That didn't work either. And so then they tried this centralized allocation system where they collected preferences and prescribed an allocation. And in fact, they weren't the only ones. There were many different medical residency sort of matches set up in various parts of the world, especially in the UK. And this isn't science, by the way. This is like sort of really the old school science layout actually looks extremely similar to the American Mathematical Monthly, which is cool. They turned out, and Roth showed, there's sort of the places that had adopted stable matching processes mostly found that they halted unraveling and they stayed in place. That includes the US National Residency Matching Program, new design in '98. We'll come to that in a moment. And meanwhile, the places that had unstable matches, mostly, it's not uniform, but mostly did not halt unraveling and were abandoned in favor of something else. We don't have much time to talk about this today, but there is this question sort of underlying, which at the time, it appeared to be the case that stability somehow helped stop unraveling, but there wasn't actually like there wasn't a robust theory to explain that. And pioneering sort of a new approach of lab experiments to teach us things that are sort of beyond what we can do with theory. Gale and Roth ran an experiment where they sort of tried what would happen if you in a lab, sort of like a completely simulated setting, you let a market unravel, and then you switch on a centralized mechanism, sort of with the variation being, is it stable or not? And what they found is the stable mechanisms halted unraveling, but they also sort of along the way discovered a pathway for why that might be the case. So it's not that people just suddenly like all decided to use the mechanism. After, so you have an unraveled market, they don't all just like say, oh, great, centralized mechanism, let's go. What happens is unraveling is imperfect, right? Some schools or students, don't manage to match. Oh, sorry, some residencies and prospective doctors don't manage to match. So those agents sort of get dumped into the centralized matching process because, why not, right? It's better than nothing. And in the market with the unstable mechanism, their experience reinforces their desire to make early matches, and so they stay unraveled. Whereas in the stable mechanism, that works out pretty well, and they decide to stick. And like, what is stability in this context, really? Well, stability means if you have your third choice residency, then your first and second choice residencies have doctors they prefer to you. And conversely, if your residency is like, I don't know, second choice doctor, then its first choice has a residency that they prefer. And so there's no incentive to get on the phone and call, sort of other programs and say, hey, I have a job, but I'd rather work with you. They're going to say, sorry, we have residents we prefer, we're not interested, and vice versa. And so stability here, right? Stability was a mathematical concept as we defined it. There is no rematching, right? Everyone has an acceptable partner, and no one has an incentive. There are no agents who mutually prefer each other to their assigned matches. But here, it has an actual meaning in the world. It means that doctors and residencies are sort of assigned in such a fashion that even if some people would prefer some other outcome, like their prospective partner doesn't want to switch. And so here we're sort of seeing like theory and practice blend, right? Like the fact that the medical residency match was running a stable matching meant that it was implementing stability in reality in some sense. Fast forward a few years, to the late 90s, and there was a new problem, which is that larger and larger numbers of doctors were marrying each other, right? There's like a significant growth in gender parity in the medical professions, and two married doctors might in fact want to match, sort of to the same city or whatever, right? They want to potentially live close to each other. And deferred acceptance, as we set it up, doesn't really allow that, right? You have remember, you have like now all the doctors walking across proposing to their first choice hospitals, doctor proposed to their second choice hospitals. There's no interrelationship between, one doctor's preferences and another doctor's preferences. And this was noted as a problem, by the way, sort of back in the earlier Roth paper. But it was becoming more and more of a practical problem for medical residency matching. And so Roth and Elliot Parenson led a redesign that integrated couples into the match. And this is a very interesting redesign because, whereas stable matchings are guaranteed to exist in the marriage model and in college admissions, and the original medical residency match are isomorphic, they are in fact not guaranteed to exist as soon as you have couples, or more broadly, whenever you have what are called complementarities and preferences, where the outcome of one agent sort of affects the preferences of some other agent in this context. But they were able to build a heuristic that sort of starts with deferred acceptance and sort of like adjusts, then integrates in the couple's preferences and adjusts a little bit, sort of perturbing the matching. And show empirically, and later we were able to understand theoretically, that in practice, this was very likely to find a stable matching. That even though couples are a problem in theory, so long as they're like a sufficiently small density relative to the entire market, maybe they're not so much of a problem in practice. At this time, they also switched to an applicant proposing version of deferred acceptance. Remember, previously they were running something equivalent to hospital proposing deferred acceptance. Here they switched to applicant proposing. And remember from our theorems earlier, that is a non-trivial decision, right? This simplifies the strategic problem for doctors, right? It means now you as a doctor just have to state your true preferences. It also means that we're picking an outcome that is sort of like more doctor preferred. Although it turns out and part of the justification for this is the strategic point was important, right? They wanted to make the problem strategically simple for doctors, but then also empirically, while in principle that lattice could be big, they found using sort of matching data that the set of stable outcomes seemed to be small. And if the set of stable outcomes is actually small, then this issue of like side optimality doesn't matter very much. And in fact, actually the incentive problem gets easier for everyone as well. Last thing also, of course, there was this question of like, could you improve outcomes? So rural hospitals often, there's sort of smaller areas had trouble filling, some of their positions often. And so there was a question of like, could we use the matching mechanism in some way to improve the outcomes for rural hospitals? And unfortunately, there's a strong generalization of that lone wolf theorem that we stated before, which is that not only, so remember the lone wolf theorem is the set of men and women in the marriage problem who are matched are the same across all stable matchings. Similarly, the set of positions filled is invariant across all the medical residency matching. So if you manage to fill 6 of 7 positions in some stable matching, you will only fill 6 of 7. You'll fill rather precisely 6 of 7 positions in all stable matchings. And worse, there's an even stronger generalization, which is that if you don't fill all of your positions, then the set of doctors you receive is invariant across all stable matchings. And so not only is it the case that if you are a rural hospital that doesn't manage to fill your positions, we can't pick a stable matching that's going to fill more positions for you, but we in fact can't pick a stable matching that is going to improve your doctor set on any dimension. It's going to be the same set. And so here, theory provides a boundary to what's achievable in practice. Right. So here practice sort of with couples matching gets around theory. There's technically a non-existence result, but in practice it wasn't an issue. Here, theory sort of gets around, sort of like blocks practice. There is no way through stable matching to improve the outcomes of rural hospitals on the margin. Anyhow, this this new algorithm with some subsequent tweaks for how they deal with like sort of doctors who don't match in the main match and so forth is still in use today. I do have the up-to-date slide, but I always like to show this one because this was back in like 2012, 2013. NRMP launches social media. It was really exciting back then, I suppose. You can now like us on Facebook and follow us on Twitter, now known as X, apparently. Today, the web design is, we're at 70 plus years of the match. The web design is a little bit more stark, at least with their current lead image banner. But the emphasis, just as it was before, is on exactly sort of what we'd be excited about as market designers: fair, equitable, efficient, transparent, and reliable matching over 70 years. So market design is about turning theory into practice, right? We had this theorem about stable matching, right? If you assign partnerships in the following way, you will get a matching that has this property of stability. And it's true in the world, right? Like, using a stable matching algorithm can produce an outcome that is stable, and that in fact is so stable that it stabilizes an otherwise chaotic market process, this unraveled market. And so in that sense, and one of the things that's magical to me about market design is that it's really about projecting theorems on reality. You don't always get to take a mathematical theorem and directly observe its function in the world. But here, by changing to a stable matching mechanism, you can implement stable outcomes in practice. And then, as I said at the beginning, all of this feeds back into more theory. So, first Imrlik and Madjian, and then Kojima and Patak showed that, in fact, when your market gets very large, the scope for anyone to manipulate. So sort of the incentives to state your true preferences start to kick in for everyone in expectation, at least under certain models of sort of sufficient mixing and preference breadth. Meanwhile, I mentioned this small number of stable outcomes in the medical residency match problem. This large market stuff provides a partial solution, and then Ashwagi, Kanoria, and Leshno sort of finished the solution in some sense by observing that if there's even a small amount of unbalance in the size of the market, that again, the set of stable outcomes collapses very quickly. And then meanwhile, this question of but how did stable matching actually stop unraveling? How does it get people to want to participate in the market? And Roth and Shore have a beautiful paper about this. And note, this is a different Roth. We had several papers from Al Roth. This is my colleague Ben Roth, who happens to be one of the sons of the former. Okay, so residency matching turns theory into practice and then spins back into beautiful new and ever deeper theory, right? These are also teaching us fundamental things about matching and about market design, and their math is very elegant and sophisticated and gets more and more so over time, right? These use a really interesting probabilistic approach. This introduces sort of a new sort of structural condition to understand market clearing mechanisms. Beautiful interplay between theory and practice. I'm now going to take us to a different application category that was sort of, evolving in parallel. Pun not intended. That will be a pun at the very end, I guess. So remember Roth and Parenson, late 90s. At the same time, Tayfun Sonmez, in joint work with Michel Belinsky, was observing that centralized matching is also a pretty good model, right? So the Gale Shapley model of college admissions is actually a pretty good model of the admissions system for centralized college admissions in Turkey at the time. But as they showed in this paper, there were a number of design flaws with the system that was being used in the Turkish college admissions system. And so they, observed, look, this fits this Gale and Shapley model. We can improve this system using deferred acceptance, and sort of proved a number of characterization results that sort of showed that deferred acceptance was, in some sense, the unique optimal solution, to Turkey's problem. That was followed, Tayfun follows that with a paper by Attila Abdülkadiroglu that looked at a number of different school systems in the United States that were using various forms of centralized school choice. So places where parents would send in their preferences for where their kids might go to school. This is for K through 12 education, and then assign them according to some priority rules. And these two papers together really set out a framework of design goals for what we might want in school choice matching. again, sort of hearkening back to Gale Shapley, but sort of painting it in different languages and pushing it further. So different language and pushing it further. So first, stability in this context really becomes elimination of justified envy. So this means if a student I envies a student J, then J has a higher priority than I at J's assigned school. So that, again, that's our old stability rule, except now stated in priority language. So schools in many school choice contexts just have a priority rule, might be given by test scores or like, walk zone versus, sort of walking distance versus not. The schools might not necessarily be strategic actors. And so, oh, sorry, there's a typo there. That should be a I subscript. So mu J is preferred by I to mu of I implies that J has higher priority at I. So now it's not rematching. And in fact, maybe we aren't even going to have, students calling schools and rematching in the same way that we imagine in the medical residency match. Although in fact, this was happening in New York. Here, it's much more about fairness, right? It's about saying, look, the priority rule is implemented as such that if you want some other outcome, then it better be the case that you don't have higher priority for that outcome than someone who for that school than someone who got it. Again, here, strategy proofness turns out to be a design goal. In a moment, we'll talk about the importance of that in the context of Boston. Pareto efficiency, this is an economic efficiency concept that basically says we can't make anybody better off through swaps. So we can't, find, sort of two sort of families that would prefer to switch their schools, trade their schools. Not equivalent to stability, by the way, in general. In very simple models it is, but in the full school choice context, it's not. And then the last condition, which Belinsky-Sonmez introduced, is respect for unambiguous improvements in priority. So this says if I make your priority ranking higher, unambiguously, sort of holding everyone else's priorities fixed, then your outcome had better improve. And if you think about it, like if the priority rules are based on test scores or something of the sort, that's a very natural condition to want. You want to incentivize students to want to improve their test scores. It shouldn't be the case that by getting a higher score, you get a worse school or a less preferred school, rather. So again, all of these conditions here harken back to classical matching, right? In fact, we didn't talk about it in detail, but people studied Pareto efficiency in the Gale Shapley context as well. Strategy proofness, that's our old incentives result. Elimination of justified envy, that's stability. Respect for priority is a new condition, but you can see it making sense in the marriage problem or in medical residency matching as well, right? Same thing there, right? You don't want doctors to be concerned that if they manage to get hospitals to like them more, then they might get a less preferred hospital outcome. These are all good things to desire. But they make particular sense in the context of school choice. Again, strategy proofness, as we'll see, parents are often not sophisticated in how they think about these algorithms. They don't necessarily have full visibility into how they run. Strategic simplicity is a value. Pareto efficiency, we'd like to allocate the resources as efficiently as we can. Elimination of justified envy, as we've said, is about fairness, and respect for improvements is about incentivizing people to want to raise their priority. And as Abdukadıroglu and Sonmez characterized, deferred acceptance, first of all, our now student optimal stable mechanism gets very close. It's actually stable and strategy proof and improvement respecting and Pareto efficient. And not Pareto efficient. The immediate acceptance mechanism, what was being done in Boston, I'll detail this in a moment, is Pareto efficient with respect to true preferences, but is very much not stable and very, very much not strategy proof. They actually also worked with a third mechanism that we won't talk about today, but you could give an entire other math science literature lecture on the history of top trading cycles, which starts with the Shapley Shapley-Shubik. Shapley. I don't remember. Sorry, I'm blanking on the paper that first introduced top trading cycles. Shapley-Shubik is matching with transfers. The assignment game won the core. And that's why we're deferring it to some future math science literature lecture. Backdrop, like you note, we have all of these various Shapley scarf. Thank you. Very good. I should shout out the name. I mean, apologies, I'm probably going to mispronounce your name. Rohit Vaish flags it's Shapley's scarf, and so I was blocking scarf with Shuvik in my head by accident, and that was the mental blocker. Thanks so much. You might wonder, by the way, we have sort of like all of these is and isn'ts. Could you get everything? And the answer is unfortunately no. So there's several different versions of this negative result. I've cited here the one from Keston, but it turns out there is no Pareto efficient and strategy proof mechanism that selects the Pareto efficient and stable match whenever such a match exists. So not only are Pareto efficiency and strategy proofness sometimes, and stability sometimes in conflict, but if we try and go for both of them, we end up breaking strategy proofness. So deferred acceptance, we've seen this before. This is actually virtually identical to the earlier deferred acceptance slide, just written now in the language of students and schools. Here, step one, each student applies to their first choice school, and each school tentatively holds its highest priority applicants up to capacity and rejects all others. At every next step, each student not currently held applies to their most preferred school that has not yet rejected them. Each school holds its highest priority applicants up to capacity and rejects all others. Iterate through this process. Again, key is that the schools are tentatively holding students. They're not accepting them until the last step. The acceptance step is deferred. This is going to be stable and strategy proof, as we've already seen. Exercise for the listener. It's not Pareto efficient. Can you find a counterexample? I mentioned that Boston was using a mechanism called immediate acceptance. What is immediate acceptance? Well, the name is sort of a hint. Shout out to William Thompson, by the way, for suggesting this name. I believe he originated. It was, a lot of papers earlier just called it the Boston mechanism. But what's really going on is instead of deferring the acceptance step is immediate. Each student applies to their first choice school, and then each school accepts its highest priority applicants up to capacity and rejects all others. Similarly, future steps, each not yet accepted student applies to their 11th choice school, and each school accepts its highest priority applicants up to remaining capacity and rejects all others. So this is emphatically non-strategy proof. What's the issue? Well, if maybe your first choice school is really popular, and so is your second choice, and so is your third choice. Well, if you apply to your true first choice school and don't get in, so you're not in the highest priority rank, then by the time you apply to your second or third choice, they might be full as well. And so maybe you don't list that first choice school. You list your second choice, or maybe even your third choice, or maybe even your fourth choice, to make sure you get a school that, to make sure you get a school that's high enough on your ranking that you really, sort of want and can achieve. Remember, that's different from deferred acceptance, where you get your best achievable outcome across all stable matchings. There's no harm in listing your first choice first, because if you don't get in, you can then apply to your second choice, and your second choice, if you have higher priority, you haven't like wasted your priority. You'll push out somebody else who will then go and apply to their second choice. This immediate acceptance mechanism has been historically very popular in practice. And sort of looking at this here, you might, sort of be wondering, but why? We've just seen all these great properties of deferred acceptance. Well, immediate acceptance sort of in principle has like something good going for it as well, which is that it's trying to give everyone their high choice, right? It's sort of like giving as many people their first choice as possible. And under that strategic manipulation we just discussed, it in fact is giving even more people their quote unquote first choice than you might think otherwise, right? Because lots of people rate, your best chance to get into a school is in that first round when none of them are full yet, or none of them have used any of their slots yet. And so, you might see people like up-ranking schools that they, that aren't maybe their true first choices, but now on paper, as submitted to the mechanism, are their first choices. And then they get in, and you can say, wow, like, look at this. Like, everyone's getting into their first choice school. Maybe we'll come back to that. But so this research in school choice also very quickly breached into practice. A redesign, we'll talk in detail about one in Boston. There was also one in New York, and there have since been ones, sort of all over the country and the world. The one in Boston really focused on this issue with immediate acceptance, right? So if you have very high priority at a given school, then you can lose that priority to the students who've top ranked the school. And indeed, this was straightforward. Like Boston Public Schools instructions literally said this: for a better choice of your quote unquote first choice school, consider choosing less popular schools, right? You can't get more clear than that, right? The official instructions at some level, recognizing this strategic manipulation. Not only that, some parents had really sort of also observed this, and even sort of tried to collect some data to understand the level of popularity of different schools. Sort of in the West Zone parents group, they stated, our one school choice strategy is to find a school you like that is undersubscribed and put it as a top choice, or find a school you like that is popular, put as your first choice, but then put a safe school as your second choice. And so here we have some parents coordinating their strategies and sort of trying to advise each other and figure out which schools to rank. But you wonder, right? Sort of what happens if not everyone has access to the optimal strategies, right? Not everyone can strategize as well or has information relevant to make the decision. And Pothlick and Sunmez have this beautiful paper called Leveling the Playing Field, Sincere and Sophisticated Players in the Boston Mechanism. Boston Mechanism, again, is immediate acceptance. And what they show is that in the equilibrium under the immediate acceptance mechanism, sincere students, in effect, lose their priorities to sophisticated students. So if you're stating your true preferences, you're, in effect, giving up your priority to the students who are strategizing. And as a result, if the sophisticated students are coordinated, via the West Zone parents group, perhaps, they all prefer immediate acceptance, right? They're in fact getting a priority bump from the fact that some other students, or rather their parents, aren't playing the strategy optimally. Meanwhile, sophisticated students prefer that their sincere students remain sincere. So not only do they like immediate acceptance, but they actually also prefer to remain, sort of to keep the group of sophisticated students small, right? The fewer fewer sophisticated students, the more sincere students are in effect giving up their priority. And so there's a sense in which there's a real equity challenge here, right? If you have inequality in strategic sophistication in Boston or in your school choice program, then the fact that immediate acceptance is not strategy proof, and particularly the way in which it is not strategy proof, means that parents aren't on a level playing field when it comes to deciding how to specify their preferences to the system. And indeed, so this was a core driver of the switch from the immediate acceptance to deferred acceptance. The Boston Public Schools strategic planning team declaring a strategy-proof algorithm levels the playing field by diminishing the harm done to parents who do not strategize or do not strategize well. And again, making that argument concrete really relies on mathematics. I mean, this is a theory paper. And how does the theory work? It uses a transformation of the market with sincere and sophisticated students to a market that looks like sort of a classical deferred acceptance Gale Shapley market, and sort of basically transformation by transforming these priorities. And so they show an isomorphism between sort of a slightly stylized model of Boston and a classical matching model, but with the sophisticated students having priority improvements. And so here, again, right, like math is part of making the case for a change in mechanism. Like matching theory is actually a path to equality of access to school choice. And that, again, like just sort of like it's beautiful and incredibly elegant mathematics, and potentially even more beautiful is the projection to reality. Given the setting of this lecture, I'd be incredibly remiss if I didn't also talk briefly about the Chinese centralized college matching process. There's a beautiful paper by Chen and Keston that looks at the Chinese college admission systems, which vary across provinces. And many provinces had been using, up until a point, the immediate acceptance mechanism, or something equivalent to it. And they transitioned to what's called the parallel mechanism, which is sort of a mixture between immediate acceptance and deferred acceptance. It's sort of like a set of rounds of deferred acceptance followed by a finalization of assignments, and then another set of rounds of deferred acceptance with finalizing assignments, and another set of rounds finalizing assignments. And so, like, if you think about it, it's, if you only do one round of deferred acceptance and then finalize assignments, that's immediate acceptance. And if you do infinitely many rounds of deferred acceptance, or arbitrarily many rounds of deferred acceptance and then finalize assignments, that's deferred acceptance. And so if you sort of switch back and forth, you're mixing between the two. And what they show, and it's an incredible set of characterization results, they show that this mixture is actually, sort of smoothly interpolating between immediate acceptance and deferred acceptance in a sense. And all of the moves that the provinces made, so like many provinces like made different shifts. They changed, like they had different level sets of layers. They had different sort of like structures. Some had a small number of deferred acceptance rounds and moved to more of them. Every move that that one of these provinces made was towards a less manipulable, so closer to strategy proof, and more stable mechanism. With a footnote, more stable here we mean sort of in equilibrium or under truth telling. And again here, so in the context of Boston and also New York, like the move to deferred acceptance was with the advice of economists, right? It was an active project that was directly informed by theory. Here, the moves were sort of informed by decision processes, in the sort of in the local governments and so forth, but turn out to be perfectly in line with theory, right? Sort of like Chen and Keston were able to find that every single one of these provinces were sort of moving in the line that theory would suggest you wanted to move. Footnote, by the way, this is the only paper in market design I am aware of that relies on a little bit of number theory. So I just have to show this result briefly. So one of the results looks at the stability comparison, and it turns out that comparing one parallel mechanism to another one, what matters is whether the sort of sequence of rounds is an additive decomposition of the other. So we've got summation symbols here. Like this is classical number theory, and if you have two mechanisms, the two different application rejection mechanisms reported, sort of given these different sequences, if S is an additive decomposition of S prime, then mechanism phi S prime is more stable than phi S. So you can check out the argument in the paper, really elegant and slick. It really involves like sort of like, tracking these sequences of rounds in parallel with each other. And so the additive decomposition basically means that you can like map one into the other. It's sort of like a little embedding theorem. But to my knowledge, this is the only paper in market design that uses number theory, much less like additive decomposition and also a little bit about factorization in any context. So that's cool. While we're on footnotes, I should note that this theory and practice of stable matching was recognized in one of the economics Nobels. There's Roth and Shapley as drawn by the committee's cartoonist, and really sort of the committee spoke in detail about this back and forth exchange, sort of like foundational theory that informs practice that goes back to theory, and so really this is a context where mathematical economics has really shaped and sort of continued, and it's in parallel continues to learn from the world. Okay, we have about 15 minutes left. And in the last 15 minutes, I'm going to take you sort of through a whirlwind, and this is a lightning round. It's going to get faster and faster and faster as we go, of what's called generalized matching. And the story of generalized matching has many different starts. Actually, one could argue it's that Shapley-Shubik paper I mentioned earlier. But a lot of people will date it to Crawford and Noor and Kelso and Crawford, which introduced job matching, coalition formation, and gross substitutes. So what's going on here Well, this is sort of like a centralized matching process we've seen before, except now also with salaries. So like, firms face a set of salaries, firms make offers to their most preferred set of workers. Footnote, any previous offer that was not rejected must be honored. That's sort of like a holding offers condition. Workers evaluate offers and tentatively hold their best acceptable. For each rejected offer, increment the feasible salary. If no new offers are made, terminate the process and implement the outcome. Otherwise, iterate. So the language here is a little bit different, but if you squint at it properly, evaluate offers, tentatively hold their best acceptable ones, iterate until we get through all of our proposals. This is deferred acceptance. But now you're not just proposing, will you match with me, but also, will you match with me at this salary? A firm might propose to the same worker many times at gradually increasing salary offers. Stated here in the language of Kelso and Crawford, under a substitutability condition, a condition that says that sort of no two workers are complements in the sense that losing access to one might make you also not want the other. The salary adjustment process actually terminates. The final allocation is going to be generically unique, and it's going to be stable and firm optimal, which makes sense because this is very close to firm proposing deferred acceptance, right? Sound familiar? This is deferred acceptance just with this additional contract term. Recognizing that relationship, you can start to now see a linkage between stable matching and auctions, right? What is stable matching with salaries? That's essentially sort of a simultaneous auction for all the workers, right? The workers are like all auctioning their position or their willingness to work for different firms. Firms are making sort of gradually better and better offers. This turns out to like link up with lots and lots of work, both in the earliest days and the most recent days of wireless spectrum allocation. The simultaneous multi-round ascending auction, all the way to the incentive auction, which actually used like an auction that's been referred to as the deferred acceptance auction. Sort of a particular type of clock auction, sort of simultaneous offers to many different television stations to recover their spectrum for use in wireless telephony. Footnote again, that was also a Nobel subject. Here we have Milgram and Wilson, who received the prize a couple of years ago. But in parallel, so now we've seen that matching can involve these contractual terms. That observation turns out to like take us much further. It opens up a massive new set of generalizations. But to get there, we have to go back to the math a little bit and like slightly reinterpret how all of this is working. So let me rewrite stable matching. Remember, our matchings were functions mu. Well, a function, of course, is just like, a set of pairs, right? It's a assignment of men and women, MW as the matched pairs. So Adaichi observed that if you, and this is a slight variation, but Adaichi observed that if you think of sort of the rejection functions, like which pairs, men and women will reject given options, you can write deferred acceptance fully generalized. And we don't have to specifically a side proposing to the other side. We can write it as, sort of, we give some options to the women. We give some options to the men from the women. We give some options to the women from the men. And the men hold their most preferred options. The women hold their most preferred options and pass them back. And we iterate, and we repeat this. It turns out that the fixed points of this operator correspond to stable matchings. And moreover, this operator is actually going to be isotone on this, this like set lattice, rather on the set lattice of the square of X. It's going to be isotone in the order of like making the men better off and the women worse off, or vice versa. And so isotone operator on a complete lattice, Tarski's fixed point theorem tells us there's actually a lattice of stable outcomes. And so we just rederived in this very sort of existential way those first theorems, right? The existence of stable outcomes, Gale and Shapley, 1962, and the lattice theorem from Conway. Well, once we've written it this way, why does it just have to be sets of men and women or pairs of men and women, right? We could add sort of arbitrary contractual terms. Formulation here is due to Hatfield and Milgram. It turns out that this whole argument continues to work so long as this isotonicity condition is still true, and so long as this fixed point correspondence is still true. And both of those hinge on that same substitutability condition, this idea that no two, now that we call them contracts, sort of man cross woman cross term, or doctor cross hospital cross term, and so forth, no two contracts are complements. So versions of this insight have been discovered several times. Kelser and Crawford actually described this idea of matching with contracts in their original paper, even though they were focused on salary matching. Tomasz Schleiner sort of found a version of this fixed point correspondence and showed that you can write these sort of like very general contract matching mechanisms with it. And then, as I said, the formulation I just gave is the Hatfield and Milgram one. But this unlocks many new applications. It turns out that matching with contracts happens all the time. So two particularly prominent applications that did redesigns based on, again, information that came out of theory. And here I have the reports on the redesigns. One of them was the U.S. Army's cadet branch matching process. So Tayfun Sonmez and Tobias Switzer rather, had sort of discovered that both the military academy and the ROTC programs in the U.S. were using things very close to a deferred acceptance like process to manage their matching, but there were sometimes subtle and sometimes not so subtle design flaws. Using the theory of matching with contracts suggested how to improve these processes, and led to a redesign, which again then fed back into yet more theory, and sort of like a really nice characterization result there. Meanwhile, the Israeli psychology master's match, similarly was redesigned in order to sort of enable many to centralize the process in a way, or sort of structure the centralized process in a way that enabled many different types of various like diversity constraints and sort of like complex preference rules and structures among the different master's programs. And where are the contracts here? Well, it's matching not just who matches to which program, but also fellowships and sort of so like financial aid type terms. Footnote, by the way, so these matching with contracts applications, really rely deeply on sort of a theory that we won't have time to get into today, but what's called weakened substitutability conditions. So Hatfield and Kojima introduced the first weakened substitutability conditions for stable outcomes and stable and strategy-proof matching. Some of my work with John Hatfield and others like Alex Westcamp is built on that. It turns out that even though that argument I hinted at here requires substitutability, you can get past it in certain circumstances that actually turn out to line up nicely or importantly with what was going on in cadet branch matching and what was going on in the different preference rules in the Israeli psychology master's match. And in particular, in the master's match, they had this decentralized process where the different programs were implementing their various design, their various like preferences over applicants. Critical to being able to do the centralization, right? In order to get programs to want to participate in the centralized match, it was really important that they be able to encapsulate the same types of preferences and diversity constraints and things that they had originally. And that really like sort of required in some sense this hidden substitutes and completion technology. But that's a story for another day. We're almost there. Once you have contracts, and again, really like once you have this formulation, nothing that says it has to be two-sided either, right? So every matching, theory and application context we've talked about so far is still a two-sided market, right? We started with men and women in the marriage problem. We got so far as cadets and branches of military service, prospective master students and master's programs. But in fact, you can go yet further. And Michael Ostrovsky, in this beautiful paper, that was his job market paper, showed that you can actually use the same generalized matching machinery to go beyond two-sided markets to these multi-layered supply chains. So now think of like a firm F selling to a firm G, who maybe transforms the good in some way and then sells the output to another firm or a customer H. And like we have a contract Y for that first transaction, a contract X for the second one. And it turns out it's the same set of ideas, right? Stable outcomes exist in, sort of in the presence of substitutable preferences, but what substitutability means is more subtle. Now it's that the underlying objects are substitutable, like, inputs are substitutes, outputs are substitutes, and inputs and outputs are complements. Footnote, again, many of the core results of matching lift to these, much more complex and sort of like more, much broader market generalizations. There's even a version of the rural hospitals theorem, but that as well, right? It's not an invariant in the number of contracts you sign, but rather an invariant in the difference in the sort of net contract flow. The difference between your number of sale contracts and purchase contracts is going to be invariant. So moving these generalizations also lets us better and more deeply understand what was the underlying mechanic that was driving the results in the simpler settings. And you can take this yet further, right? Those were vertical supply chains. You can, in fact, so long as you're willing to also allow transfers and some pricing, even take matching to multi-layered trading networks where agents are both buyers and sellers. And here, there's a beautiful correspondence that arises between stable outcomes and competitive equilibrium. Again, sort of under a suitably generalized substitutability concept. So once you get to this like fully broad trading network where agents are buying and selling from each other in many directions, possibly many contracts all at once, we realize that we've sort of come home and in some sense like harken back to an even earlier era of economic theory and sort of like plugged back into general equilibrium. As I said, in the prior generalization here as well, many of the other results lift as well. That connection with general equilibrium ties in with sort of other work that had been done earlier on markets with indivisible goods. Here again, interestingly, one of the like underlying machinery pieces used Kelso and Crawford. So this research on what's effectively general/competitive equilibrium leveraged matching theory to understand sort of like how you can allocate sort of indivisible objects. This gross substitutes and complements idea sort of, as the same sort of idea I described in the supply chain network framework also shows up in that context, a really elegant paper by Sun and Yang. And then you can go even further. So Fleiner, Jagadisan, my former student, now teaching at Stanford, Janko and Teitelboim, showed that you can actually go to even more complex markets. You can study trading networks with frictions and so forth. And oh my gosh, we are almost out of time, but this will take us to one more application context, which is peer-to-peer energy trading. And so here you actually have these like, back and forth, like multi-layered bilateral networks. I don't have time to talk you through the full abstract, but the punchline is that substitutability ensures a distributed price adjustment process can be used using only local agent decisions and agent-to-agent communication. So even this very big complex market, you can implement things that look like stable outcomes, or that are stable outcomes. You can implement stability through sort of local adjustments in some sense. So peer-to-peer energy trading, we've gone all the way from like, an abstracted model of marriage to, sort of complex energy trading networks. An observation, and this has been sort of like, for me, like one of the most extraordinary experiences of working on matching market design is that as you get deeper into this theory and sort of expand to more and more general models, you start to realize that and sort of see matching everywhere. So if you've read this talk, if you've attended this literature talk and would like to go read some literature, let me start by recommending to you Two-Sided Matching, a study in game theoretic modeling and analysis, Roth and Sotomayor. This book is one of the classics of matching theory and holds up extraordinarily well. Like every sort of I go back and reread it like every couple of years. Like it's just awesome. Very accessible, really great, beautiful math. Can't recommend it highly enough. Let me also flag, just if you're excited about matching, there are many more application areas that I haven't even had time to touch on today. So if you're excited about this and want to go think about more, First of all, there's this massive area of work on kidney exchange and now also liver exchange, sort of like various like centralized organ allocation markets to try and, literally, to literally save lives through matching. You find incompatible kidney patient donor pairs and swap with other incompatible pairs, or more broadly, manage like sort of pay it forward kidney chains, where, you might have a donor who has a kidney from a non-directed donor, a patient who receives a kidney from a non-directed donor, and then, sort of their prospective donor who is incompatible then, pays it forward and matches with a new patient. This stuff was also very first order in questions around vaccine allocation and other sort of like scarce medical resources at the start of the pandemic. Refugee resettlement matching, another one of these contexts I've had the honor to do a little bit of work on. Also online marketplaces, like one of the most fundamental papers in our understanding of online advertising auctions, sort of basically teaches sort of discovers the ideas through isomorphism to deferred acceptance. Also, of course, contexts we naturally think of as matching, like rideshare or maybe online dating. The list goes on and on and on. Matching is everywhere, and that means we can use theory to improve markets everywhere. Just to close, I want to take us actually back to Gale and Shapley. So this is, a screenshot of the first part of their concluding remarks. The reader who has followed us this far has doubtless noticed a certain trend in our discussion. In making the special assumptions needed in order to analyze our problem mathematically, we necessarily moved further away from the original college admission problem, and eventually, in discussing the marriage problem, we abandoned reality altogether and entered the world of mathematical make-believe. The practical-minded reader may rightfully ask whether any contribution has been made toward an actual solution of the original problem. Even a rough answer to this question would require going into matters which are non-mathematical, and such discussion would be out of this place in a journal of mathematics. This is, after all, the American Mathematical Monthly. It is our opinion, however, that some of the ideas introduced here might usefully be applied to certain phases of the admissions problem. And so, even back in 1962, Gale and Shapley were interrogating this sort of tension between mathematical make-believe, right? Sort of like, theory and the potential for practice. And I've always thought this line was somewhat prescient, right? This paragraph sort of saying, look, we built this abstracted model, but also maybe it can tell us something about the future and how the world should work. And as we've seen today, it indeed did. Later in the conclusion, they observe, look, everything here is simple, right? You can literally like just sort of explain it without any symbols at all, like, and it's very much stated in dialogue with reality and with sort of like the sort of practice. So what then, to raise the old question once more, is mathematics? And I'll pause there to wrap up. QED.
Well, good talk.
Thank you so much.
Are there questions?
Perhaps may I have a question?
Please.
Scott, how much do we know about how hospitals came up with those sophisticated algorithms before mathematical economists designed them? Economics is often criticized for proposing solutions that are too sophisticated for real people actually to implement. And here we have a clear example of how the opposite happens. It's a really interesting story.
It's a great question. So I don't actually know the details of their deliberations. I know that they reached the decision to try and implement a centralized matching process, and then they used a slightly different system for the first year and then switched to this one. I don't know. And in particular, the other thing, I guess, is we know that many different, jurisdictions, essentially, like many different like places and residency groups, reached versions of stable matches independently. And there were often slightly different algorithms that all produce stable outcomes in the end. So I don't actually know how they came to define them, but I do think what's possibly leading, just intuitively to me, like what might lead you here is that it starts from a very simple place, right? The same thing, you can imagine easily how you get to immediate acceptance, right? The immediate acceptance mechanism, you say, well, let's like have people apply to their first choice school, give them as many as that, fill as many slots as we can and move on. But if you notice that then some people, when they apply to their second choice school, have very high priority, like they should get in, but they can't because the slots are filled, you now think, okay, wait, how do we fix that? And so, and in fact, actually, we've seen some school systems like, sort of make that change for that explicit, or versions of that change for that explicit reason. And so my conjecture, again, incidentally, if anybody in the audience like knows, I'd love to have you shout it out, I guess, in the chat or whatever. But my conjecture is that if you assemble a committee to think of a mechanism and they arrive at an idea that looks like immediate acceptance, it's not too much of a leap to realize that you want to address this issue of like, sort of a second pool of like, whoever gets rejected in the first stage should maybe still be able to get their second choices. And that leads you to a thing that looks kind of like deferred acceptance. And again, these various implementations were not actually like deferred acceptance per se for the most part. So it's not quite, that explanation also can't quite be that simple, but like, my guess is it was arriving at wanting to fix that particular problem. And certainly we have seen in school choice explicitly that pushes in the direction of deferred acceptance often.
So it sounds, from decision-making perspective, sounds a bit like trial and error.
Yeah, exactly. And often, right. And, and that was, again, what happened in many places, including in the NRMP, back when it was the NIMP, right? They tried a first version and then they switched to, what turned out to be equivalent to hospital proposing deferred acceptance, sort of in a next round. So you sort of have to first decide, okay, we want to run a centralized system. Then you have to think about a possible solution and maybe even, view data and think, oh, wait, hang on, this has this weird sort of pathological outcome. Let's try and redesign it. So there's I'm looking at the Q&A. There's an administrative question about the recording. I do believe the recording will be available later, right? Awesome. Yes. So there will be a recording. Then there's this question. So there's this question, are centralized markets suggesting a cartel? Is it a coincidence that medical residents have some of the worst working conditions of any profession? First of all, I should say I'm not a lawyer, much less an antitrust lawyer. And so none of the, and none of these are formal opinions about the antitrust state of medical residency. First of all, the medical residency match actually was looked into as a potential, as a potential antitrust question. And sort of the ex post determination was that it was not encouraging, that it was not supporting he was not supporting like price collusion or something of the sort. Incidentally, there are theory papers about that as well, which is sort of a whole different story. But the other thing is that sort of subsequently, Nikhil Agarwal did some empirical analysis and sort of discovered actually that sort of the benefit of residency, especially like top residency programs, is so high that like if I recall correctly, the net sort of like the empirically estimated like optimal tuition for residency programs or optimal like sort of salary for residency programs is actually negative. That basically there's so much value to the training that comes from a residency, again, especially a top residency towards your future career. Again, apologies if I haven't looked at that paper in 10 years, so I'm sure I'm like missing some of the nuance and detail of the results. That basically actually, if anything, we might expect residency wages to be lower than they are at the moment, which again, sort of, makes it less clear. So first, the antitrust investigation around the medical match concluded it was an issue. There's theory, incidentally, also that suggests that like, sort of the pricing impacts of centralized matching are at minimum unclear. But also in particular in the context of the residency match, like, maybe, if anything, maybe lead to price increase, sort of wage increases relative to par. But then also like, the value of the training in residency is actually like very high. And so probably part of the issue, again, I've never been a medical resident. I can't speak to the specific conditions of residency programs as expressed in the question, but likely a lot of it is that they're packing a very large amount of content and activity into a small period, and that the long run return to the doctors for participating in that is very high. And so the market might set that as somewhat chaotic. I don't know. Further questions?
Okay. Well, let's thank Scott for a really beautiful, beautiful talk.
Thank you.
And the next
Thank you
talk
again
in
for
the
having me.
series will be in February. Thanks again.
Great, Scott. Good talk.
Thank you so much.